It's math and bass. Yeah, it's time for another video. We're gonna do a video right now on piecewise defined functions. Let's get to it. To begin with, we are going to review what one of the most elementary piecewise defined functions is, even if you didn't know it was piecewise, and that is the absolute value function. So, a lot of times we think about absolute value in terms of a number. By definition, the absolute value of a number is the distance from 0 to that number. So, if I moved from 0 out to some number, say x, then I would have a distance of x units. X units. And if I moved out from 0 to the left, for say, to some negative x, I'd also be walking a distance of x units. Both of these show us what the absolute value of a number is, and that is the absolute value of some number x is just the distance from 0 to x. Hence, if I walk to the left, if I walk to the right, if I walk x units from 0, I still walked x units. In other words, distance units can't be negative, so we define the output of an absolute value of something to always be positive. You can see already on the screen that we have the absolute value of a function given to us as a rule, and that is this rule right here. So we're going to have to think about what this rule means. But before we do, we can go ahead and just plot the function. And we could do this by filling in the table of values that's given to us to the left here. So if x is negative 3, the absolute value of negative 3 is 3. If x is negative 2, then the absolute value of negative 2 is 2. Go ahead and plot those 2 points real quick. When x is negative 3, the output is 3. When x is negative 2, the output is 2. If x is negative 1, the output is 1. If x is 0, the absolute value of 0 is 0. And then if x is 1, absolute value of 1 is 1. If x is 2, absolute value of 2 is 2. And if x is 3, the absolute value of 3 is 3. So we can start seeing the pattern there on the graph. And indeed, it looks linear on both sides of 0. So I'm going to go ahead and draw those lines using my handy little tool here. Draw that line right there. Make sure it's just as accurate as can be. And then we're going to draw the line on the other side as so. Again, I'll make it nice and accurate. And we see the graph of the absolute value function. Looks like a little V or something. And so that's great. But how does that graph relate back to the claim definition above? Notice above the rule absolute value of x, which we're calling f of x here, which we just graphed. It's actually defined to be two different rules depending which value of x you are given. And that is, notice in this rule right here, if you are positive value of x or 0, then your output is just x. And we saw that. If x was 1, the absolute value of that was 1. If x was 2, the absolute value of that is 2, and so on. That is the part of the line on quadrant 1. So in quadrant 1 over here, this is the graph of the function y equals x, and that's true if x is not negative, bigger than or equal to 0. Now, if x is negative, then we have to turn it to a positive, just like we saw up there. So to do that, if we have a negative number x and we negate it, then it would become positive. Hence, if we have a negative input x, we take the negative of that to turn it positive. So that gives us the line on the left, y equals negative x, and that is true for negative values of x. We saw that. If x was negative 3, then the absolute value of that was positive 3. Negative 3 is 3. If x was negative 2, the absolute value of that was 2. Negative 2 is 2, and so on. So we actually have this one single function here, the absolute value function, and it is defined by different rules depending on which value of x you plug into the function. It's an elementary function, and it helps to give us a little intro into the overall general discussion about piecewise functions. So in this little statement below, the absolute value function, what we just looked at, it is an example of what we generally call piecewise defined function. So now we're going to go look at what that is in general. Piecewise defined functions. Let's go line by line here. Start in this line. Definition. Piecewise defined function. It's a function that satisfies different rules or formulas or whatever it is on different intervals on its domain. So it behaves differently depending on which input you're talking about. We just saw the most elementary of these types, and that is the absolute value function. Now, it's always defined. No matter which x value we plug in, we can find the absolute value of that. Hence, the domain is all real numbers, from negative infinity to infinity. But we did see a moment ago that if x was not negative, if it belonged to the interval closed 0 to infinity, then the function's rule was x. But, however, if x was a negative number, then the rule for the function was negative x. And hence, we wrote this entire rule. F of x was the absolute value of x, and it was x if x was not negative, it was positive or equal to 0, and it was negative x if x was negative. This type of way of writing a function is an example of how we write piecewise defined functions. So furthermore, here's the generality. Let's suppose we have a function, call it f of x, and it has, k different rules, rule 1, rule 2, rule 3, and so on, and eventually rule k. And those are defined on different values of x's, different intervals, which we're going to correspondingly call I1, I2, I3, and so on all the way to ik, such that the first interval I1 corresponds to the first rule, rule 1, and second rule I2 corresponds to the second rule, I2, and all the way down to rule k corresponds to some interval of x's I sub k. In general, we write the function like so. Just like before, we wrote the absolute value of x. It was x if x was positive or 0. It was negative x if x was negative. You see there, that's like your rule 1. And right there, that's like your interval 1. Right there's your rule 2. And the interval 2 for which it's defined. It could have many. It could have 3 rules, 4 rules, and general k rules. Just so happen to be the absolute value function has 2 different rules. So when we graph such functions, we got to graph each of these rules over the specified domain for which it's given in the rule. Let's look at an example to help us understand this even more. Let's pick blue. All right, we are going to graph this function here. F of x has 3 different rules. The first rule is x squared if x is less than -1. Then it is behaving like just the number 3 for values of x between -1 and 2. Notice that it's defined to be 3 at x is -1, but not at 2. And then finally, it's x if x is bigger than or equal to 2. So we'll just run through these one by one. Rule 1. Rule 1 is x squared, and that's true only for values of x less than -1. So I know what the graph of x squared looks like. It's the square function. We could plot some of these points. For instance, if x was -2, then -2 squared is +4. If x was -3, -3 squared is +9. We could keep going if we had more space. And then it's going to behave like this function all the way down till we get to x is -1. When x equals -1, though, however, you got to remember that it actually switches rules. So it's going to behave like x squared all the way to -1. So we're going to keep going down, down, down until we get to -1, but it actually doesn't have a value there for this rule. So we draw a little circle to indicate that it's not defined to be this rule at -1. It's kind of a nasty looking picture I just drew. Let me redraw that a little bit. Loop-de-doo. That's a little better. Big old arrow up there. How pretty. All right, that's the first rule. That is the rule x squared for x less than -1. Right? To the left of -1, it is behaving like x squared. Second rule, rule 2, is the rule just 3. And that's true if x is equal to -1 and all the way up to 2. So now actually at x is -1, we're going to draw a dot at 3 as the output because it obtains that value there. When x equals -1, the rule is 3. And then it's going to behave like 3 all the way in between -1 and 2. But once again, once we get to 2, we don't have a value there. And so it switches rules. So we put the little open circle looking thing, the hole. It's going to switch rules. It's now going to behave like the third rule when x is 2. And that rule is it's just x. And that's true if x is equal to 2 or bigger than 2. So at 2, the rule is x. If x is 2, then the output is 2. Dot, draw a dot, it obtains that value. When x is 2, the output is 2. When x is 3, the output is 3. When x is 4, the output is 4. And so on forever. It behaves like that line. You see the 3 rules there. You see x squared to the left of -1 for x. It equals 3 for values of x between -1 and 2. And it equals to x if x is bigger than or equal to 2. The entire graph we see there is the graph of our piecewise defined function f of x. So this is the kind of procedure you got to go through every time you graph a piecewise defined function. Let's look at a couple more of examples just to get a better idea. All right, a couple of examples here, f of x and g of x, both piecewise defined functions. Let's start with f of x. Let's use a different color. Let's use green. For values of x less than 1, this function is defined to be 1 minus 2x. The line with slope -2 and y-intercept 0, 1. So that's strictly less than 1. It doesn't happen when x equals 1. So I go to 1. If I were to evaluate that at 1, notice that 1 minus 2 times 1 is 1 minus 2 is -1. And so I'm going to draw a hole, a little circle at 1, -1, because I know it only behaves like this to the left of 1. If x was 0, we'd be at 1. If x was -1, we'd be at 3, and so on and so on. I get that line there, like so. That is the line y equals 1 minus 2x, and notice it's only true for values of x less than 1. We then switch rules to square root x. Notice it's also not defined to be this rule at 1. See, it's strictly bigger than 1 there. So in fact, this function doesn't even have an output at 1. If though, however, we graph the graph of y equals square root x, then at 1 we would be 1. So it starts there but not equal to. If x was 4, we'd have an output of 2. Remember what the the square root function looks like? Looks something like that. But notice it doesn't do this forever. It stops at 4. So instead of keep going, we're just going to stop at 4. And because of the equal part there in the interval for which it's defined, then I know there's a dot at x is 4, comma 2, because we obtained the value of 4. It finally switches rules to 2x minus 1 if x is bigger than 4. If x was 4 here, then 2 times 4 minus 1 is 7. So I would get the point 4 comma 7, and I'm going to draw a little circle there again because we don't actually have this rule when x is 4. It's only to the right of 4. That's a line with slope 2. Move over 1 up 2, get another dot. We could draw that line forever. So there you go. There's the graph of f of x in this case. Finally, we'll pick one last color here. How about pink? G of x. We got this 3 different rules. X plus 2 of x is less than or equal to negative 1. X squared for values of x between negative 1 and less than or equal to 1. And finally, cube root x if x is bigger than 1. So for the line x plus 2 equals to y, I know for that rule that if x was negative 1, negative 1 plus 2 is 1. And hence, I go to negative 1, and the output is 1. If x was negative 2, then the output would be 0. We get the line x plus 2 for values of x less than or equal to negative 1. The place where we're changing rules here, x is negative 1, we obtain that value at that dot because that's where it's defined to be. Then it becomes x squared. Now, notice in this rule, if x was negative 1, the place where we're switching rules, negative 1 squared is 1. And in fact, that's the same place where rule 1 ended its rule. So that place right there, negative 1 comma 1, is actually a location where we're switching rules and becoming another, and they happen to be in the same spot. And there's nothing wrong with that. So I know what the x squared graph looks like. It's a parabola through the origin, like so. Draw a little closer. So it looks something like that. Man, it means to be more curvy. Hold on. Yeah. Nice. So there you go. There's the graph of y equals x squared for values of x between negative 1 and 1. And notice again, at x is 1, we have an equal part of this, so we include that on this portion of the graph. Finally, it's cube root x. Cube root x. Hopefully you remember what that looks like. Notice that if x was 1 here, cube root of 1 is 1. So again, at 1 comma 1, we're going to continue to follow the same rule. The next perfect cube root is when x is 8. Cube root of 8 is 2. So it's that very slowly increasing function that looks very similar to square root. It looks something like that. Hence, we get the graph y equals g of x. And there you go. We saw 3 different examples of piecewise defined functions and an intro with the absolute value function. So I hope you learned a little bit about the introduction to piecewise defined functions. Mostly we just practice graphing them, defining them, what they are, the basics. But there's going to be a part 2 of this video. So look out, because we're going to do some more, including, given a graph, can we extract the formula of the function? And we'll also look at some applications. Okay, now, we gotta do something. We gotta do Bates States. Yeah, peace.